So in this example, we're being asked to consider the conservation of momentum in an isolated system with an astronaut and a wrench. An astronaut is floating in space 100 meters from her ship. So there exactly we have a distance of 100 meters. She and the ship are motionless relative to each other. The astronaut's mass, including the spacesuit, so that's our first mass, are 100 kilograms. And now the mass of the wrench is 1 kilogram. And she has a 20-minute air supply. So we put that the time is 20 minutes. She devises a plan to use conservation of momentum to get back to the ship safely by throwing the wrench away from her. So first we're being asked in what direction she should throw the wrench. What is the magnitude of her recoil velocity if she throws the wrench at 10 meters per second? So that's a velocity we can work with. And will her recoil velocity be great enough to get her back to the spacecraft before she runs out of air? So will it be less than 20 minutes? So to understand this problem better, I'm going to do a before and after diagram. So for the before, we can kind of draw out the situation. This is our astronaut, and she has her wrench, and then this is the ship. And she is 100 meters from the ship, and she is moving away in this x direction. So now after, the ship is still here, and ideally, this first question we have here is what direction she should throw the wrench. She should throw the wrench away from her, and then this will propel her towards the ship. So what we're trying to find is like what velocity is she gonna get to the ship, her recoil velocity. And now the wrench will be moving in this x direction away from the ship. So the first thing we can do, since we already know that the direction of the wrench is away from the ship, we can solve part B. What's the magnitude of her recoil velocity if she throws the wrench at 10 meters per second? So we could use a conservation of momentum equation here. We have the mass of the astronaut times the initial velocity of the astronaut, and then plus the mass of the wrench, initial velocity of the wrench, and this will be equal to mass of the astronaut, her final velocity, plus the mass of the wrench, and the wrench's final velocity. So in this case, we can further simplify this equation. Okay, we know that your initial velocities are 0, so we already know that this whole part of the equation is going to be 0. So now we can simplify this, and we only have this side to solve. So we're looking at the final velocities in this case. So now if we move around this final velocity of the astronaut, which is what we're trying to find, our equation looks like this now. We would have the negative mass of the wrench times the final velocity of the wrench times the final velocity of the wrench, and then that would be over the mass of the astronaut. And now we can start plugging values in because we have a more simplified equation. We know that the mass of the wrench is just 1 kilogram, so we can plug that in. And the final velocity of the wrench that we're being told here is going to be 10 meters per second. And then the mass of the astronaut, we know that it's 100 kilograms. So these kilograms will cancel out, and ultimately we get a final velocity of negative 0.10 meters per second. And this makes sense because she's moving towards the ship, and that's her recoil velocity. And now, let's try to find out if her recoil velocity is great enough to get her back to the spaceship. So we do need a different equation for this. Let me make some space on the board. So for this, we're going to need a different equation, and it's going to use the distance. To find the distance, usually, we have to multiply the velocity for the time. But in this case, we're trying to find the time that the recoil velocity is giving her. So to get the time, we just rearrange this equation, and it'll be the distance over the velocity. And once again, we have both of these values. We know that her distance is 100 meters from the spaceship, And we now know that her velocity, her recoil velocity, is 0.10 meters per second. And we won't put the negative value because we're working with time. So once we cancel out both of these values, her time is 1,000 seconds. And this doesn't really clarify because we know that she has a 20-minute air supply. So let's convert this to minutes. 60 seconds, 1 minute, and she has 60 minutes. So she does make it to the spaceship before her air supply runs out, and she has an extra 4 minutes.